So I found a flash drive in the lab. It says, what does it say on it? It's yours. A little bit. Well, the only piece of paper I looked at, virtual piece of paper I looked at on the drive, had 2 names on it. I only recognized one, but cheers. So had a couple of ideas for final projects. One of them is on the Facebook page. It is a guy on campus who's trying to build intelligent trash pails so that you can read it, so they know when they're full and they signal that they have to be emptied. And they'd like to do some wireless, embedded wireless for the trash pails. Some sensors to tell. I mean, how do you tell a trash pail's full? What does it mean to have a trash pail full? Well, is it weight? Is it volume? Is it, what is it? Volume, probably. How do you detect volume? I don't know. So that's one possibility. Another one we were just talking about is I'd really like a little synthesizer, something that's about this big that could be painted up in camouflage. But when it hears a gunshot, I have hunters come hunt on my property. I don't like it. So I want this thing, when it hears a gunshot, I want it to scream hideously. I think that'd be funny. Maybe it's my twisted sense of humor, but... So it's got to have a really realistic sounding human scream. Yeah. Any questions about Lab 1? Type volatile. What does type volatile do? Type volatile means that it tells the compiler that the variable can change without warning. And that means that, and it's used for communication between interrupts and main. If you find, geez, that's funny, time 1 never seems to get incremented or decremented, it's never reading anything in main. I never get entry into my function. It's probably because you forgot to declare it volatile. And any variable in main which is only read and never written is eliminated. It is optimized away. It does not exist in the program. One way to check for this, in fact, one way of finding weird errors like this in general is to whip open the .asm file and look at the assembler listing and see what code was actually generated by the compiler for each statement. You can read it pretty easily. It's not as daunting as it sounds. Any other questions about Lab 1? I was quite surprised that Lab was full yesterday on Super Bowl Sunday. Pleased, but surprised. Yes?
For the, when we're generating a random number, why is it every time you start up a program you get the same number?
Why do you get the same number? Did you start with the same seed?
You just call it rand.
You just call the rand function. The rand function assumes some seed. It always generates the same number if it has the same seed.
So how do you feed it?
How do you feed a seed? Well, how do you generate... so what is there about the machine that is unpredictable and therefore are irreproducible? The time to boot into the program, the time to from reset until the code starts is cycle accurate, right? So you're not going to get any kind of random number out of that. What is quite, however, random is the time at which the human pushes a button. So let's say you had a counter, an 8-bit counter running in main, just as fast as it'll go. So it's counting at maybe a half a megahertz. So it's overflowing 1,000 times a second. Right? It's an 8-bit counter. It's overflowing 1,000 times a second. When you push the button, you take the state of that counter and use that as the random number. It now becomes a very good random number, between 0 and 255. Why use the stinking rand function? You have a perfectly good random number generator right at the end of your finger. The other question? Back? The debounce code I gave you works for exactly one button. Oh. The debounce the debounce program had two functions in it. One function is debounce, the other is not. So button 0 was, I think, was not debounced, and button 1 was in the code. That was for comparison between the two. 30, 50, something like that. You can test it. It should be responsive without missing, responsive but not miss events, right?
Yeah, like we are told, like if a string is stored on flash, we should use copy string to LCD. If the string is stored on SRAM, we should use LCD string. But one kind of issue is like if you use sprintf to, for example, like constant string, your result, that's a constant string. If I store that on the flash memory, and also the technique that constant string with like the real action time.
Don't store it in flash.
Okay.
By default, sprintf puts that literal string, the format string, in RAM.
Okay.
So it'll work.
Okay.
Anything else? So I believe that either 3 or 4 groups finished last week. How many people finished yesterday or got to the point where they could? Good. All right, so there's progress yesterday. So the Sunday session, you like Sunday session? Apparently a lot of people liked it because it was flat full. The room holds 42 people. That's half the class. I'm very amazed. But probably some people left in time for the Super Bowl anyway, right? Okay, Lab 2. No more questions on Lab 1. Let's move to Lab 2. I started talking about Lab 2 last time. I want to redraw it in a little more detail because I sort of gave you just the overview last time. And the circuitry external to the CPU is going to be minimal. You, of course, are going to have an LCD because that's how you read out the digital voltmeter. You're going to have a keypad in this case rather than the STK500 buttons, and we have to talk about that. And this is partly to get you used to the idea of scanning a keypad. So we're going to have the LCD. By the way, that suggests that after you finish this lab, don't take apart the LCD circuit. You're going to need it next week, or you get to build it again. So the specific circuitry we're going to use for the digital multimeter is we're going to have some digital multimeter probe. This is going to be the probe you use to hook to the device under test. And before we go into the ADC, we're going to do a little protection stuff. This may or may not be completely necessary, but it's really good form when you might put a voltage which is too big into a port pin. How could you put a voltage that's too big in? Let's say you hooked it to the signal generator and the signal generator is turned up to 20 volts. You turn on the signal generator, that port pin doesn't exist anymore. All right, so we're going to use a 1K resistor and a pair of diodes which are called snubber diodes or clamp diodes or clippers or whatever you want to call them. The 1K limits the current to something reasonable, and the diode shorts any voltage above VCC plus 0.7 volts to VCC, and any voltage below minus 0.7 volts to ground. So this is a pretty good protection of an input. The input to the actual internal circuitry of the microcontroller includes a pair of diodes, but they're fairly small. They're easy to burn out. You're going to use 1N914s here, which I don't think you can burn out with anything in the lab through 1K. But watch, somebody will prove me wrong. This is then going to go into one or more channels of the A to D converter. And also to port B.2. This is A.0 and A.1. Into port B.2, which is internally connected to a comparator. We're going to talk a lot more about how the comparator is connected to timer 1 in a few minutes. And then B.3 is going to be connected through a voltage divider to VCC, where these are maybe 10K each or something of the sort. So this B.3 is going to be set to VCC over 2, obviously. And so the comparator will transition output from positive to 0, from VCC to 0, whenever B2 transitions across the voltage VCC over 2. What's the input impedance of the A to D converter? Good question to ask the data sheet. You should. Now there's also going to be probably at least 2, probably 3 resistors that go to several other pins. Maybe, how about B5, B6, and B7, doesn't matter. And let's make these 1K, 10K, and 100K. These are going to be used to selectively inject current into the device under test if you happen to be in resistance measuring mode. So if you're measuring resistance, the way you're going to do it is you're going to connect these to 5 volts using the output drive pin, the pin drive. Set these to a high voltage. That'll drive current out through the resistor that you've presumably attached to the digital multimeter. And by reading the voltage here and doing a voltage divider equation, you'll know what this resistance is. Because you can choose which of these pins you want to turn off or on, you have the ability to auto scale. You get best sensitivity for a measured resistor if the resistance under test is not more than 9 times bigger than the resistance and not smaller than 1/9 of the resistance or so. Actually, you get best sensitivity if this resistor is about the same as this resistor. So for small resistances, and you have to measure from 100 ohms to 100K, for small resistors you're going to want to use this. You want to turn on B5. For big resistors under test, you want to turn on B7. The way you turn off a resistor, the way you turn off one of these ports is you make it an input, and therefore it goes to high impedance. It draws no current. It's like turning off the switch. So it's either going to be, the outputs here are either going to be output and high or input and low. We're going to use the output of the comparator to trigger a capture on timer 1, and we'll talk about that in more detail. This is going to trigger a capture on timer 1. Going to use this circuit to measure frequency at the applied at the device under test. So again, you're going to have to auto scale. You're going to have to auto scale the measurement of time, of period here, of the waveform. How would you auto scale that? Change the divider, change the clock divider, the prescaler. Right, so for very high frequencies, you're going to want to run the prescaler at a divide by 1. For very low frequencies, you might want to run the prescaler on a divide by 1,000. So that you always are counting up a reasonable number of ticks. If you want to get 1% accuracy, you have to count at least 100 counts. Right? On the other hand, if you count more than 16 bits worth, 64,000, you overflow. And so you have a limited dynamic range. It's a fairly large dynamic range of frequency, but you probably will need to auto-scale that. Auto-scaling the input voltage can be done in a number of ways. What I'm going to ask you to do for this lab is to change the reference voltage to which the input voltage is being compared. So you can set full scale ADC can be set to 5 volts, 2.56 approximately, or about 1.3 approximately, and every chip is slightly different, so you'll have to calibrate this, and that's annoying, but that's the way it is. The 5 is accurate within a % or so because that's AVCC. Comes right off a voltage regulator. The 2.56 comes off of some internal voltage reference, which is good within about 10%. You have to measure voltages within 2%. Therefore, you will have to calibrate it, most likely. And the 1.3 is probably about 5%, but you better check that. So you're going to choose the full scale. If the voltage is big, if it's greater than 2.56, you better choose 5. If you set the... So what's the procedure? How would you auto-scale, rationally auto-scale this? Jeremy?
If you start it so it's always at 5 and then just check what the voltage is, and if it's less than 2.56, then you can change the scaler and remeasure it?
Yeah. So you could, that's right. So you'll step down. So if you get less than 2.56, you're going to get better accuracy if you change full scale to 2.56. Because in all cases here, you get about 10 bits out. If you're really, really obsessive. If you're not really obsessive, you get 8 bits. What does it mean in this case to be really obsessive? It means to put the CPU into ADC sleep. You set up the conversion, you stop all of the internal processing, which cuts down the digital noise, you read the value, and then you turn back on the processing by having an ADC done interrupt. You take the ADC done interrupt. This turns off the CPU for 100 microseconds. That's forever. Well, for some applications. For this application, it's just fine. So you must use ADC sleep if you want to get 10-bit accuracy. Otherwise, to get 8-bit, you have to be a little careful, but not too bad. I'm only asking you to get 7-bit. So, any questions on this? This is the more detailed setup. Jeremy?
For the calibration, do you want us to have a calibration script that you run with LCD screens for the value of the keymon or something like that?
Ooh, that'd be good. I like that. Yeah, you could do that. I guess the manual way of doing it would be to say apply a 2 volt, exactly 2 volts to the input and press go. Now apply exactly 1 volt to the input and press go, and then you could calibrate this scale and this scale. This one you don't need to calibrate, probably.
I'm still a little confused, but what do you change the actual pre-scaler value for measuring the frequency, auto ranging the frequency?
Well, let's say that you start at some random pre-scaler. There's 3 possibilities. One is you measure no counts at all. Uh-oh. It's too high a frequency. It overflows. Uh-oh. Or it's just right in the middle. Now, and you can turn on an overflow interrupt. And so the CPU will tell you if it overflows. And that's very nice, because there's no other obvious way of telling. So what would I do? Would I start slow or fast? I don't know. Maybe probably start in the middle on that one and do binary search, maybe. Circuitry's easy. Just resistors, a couple of diodes. Of course, you do have to wire up the LCD still, and you're going to have to connect a keypad, a 16-pin keypad, which we're going to have to talk about. It's a 4x4 grid of switches. So there's a grid like this, a 4x4 grid, and every intersection has a possible switch point on it. And you have to be able to decode that. We'll talk about that code in a little while. So let's talk about timer 1. Because timer 1 now is the timer which has the capture feature. It has the ability to detect a rise, a fall, or a toggle on a given input bit, and to store the time of that transition in a special register. Yeah, comment? Question? Yeah. So let's build a diagram of timer 1. It's pretty similar to timer 0, but instead of, so there's the usual 8-bit bus that feeds everything, and then there's a T count 1, name of the register, but it's a 16-bit register with an 8-bit connection to the bus. Oh man, what does this mean? This means that you have to take 2 bus cycles to write the 16 bits to T count 1, which is the timer 1 timer. And because it's time that we're interested in here, you want to make sure those 2 writes or reads appear to be simultaneous. Right? You can't read a byte, wait a few cycles, read the other byte, and expect to get a correct time. So, when you ask to read this register, whenever you read the low byte, it copies the high byte into a special place and saves it until you read it. And so you get a synchronous read, a synchronous 16-bit read. Now, carefully listen. It stores the 8-bit high until you read it. If you never read it, you never read another value again out of that register. If you expect to read a 16-bit value, you must read the high value. If you don't read the high value, if you read the high value first, then the low value, the timer is frozen forever. You have to read the low value, then the high value. If you just use the 16-bit reads that are built into C, you don't have to worry, because it does the right thing. There's also a OCR1A, output compare register 1A. This works like the timer 0 compare register, except again it's 16-bit compare. This can be an interrupt source. It can also go to a waveform generator, which goes onto pin D.5, which is OC1A, logically speaking. There is an OCR1B, which also does an equality measurement with T count 1. Is also an interrupt source. Can also generate a waveform off of D.4, which is OC1B. So far you say, oh, that's boring. It looks just like a big version of timer 0. But there's another register, which is the important one here, which is the ICR1. This is the input capture register. And this takes a copy of T count 1, which is clocked in either from the analog comparator or from ICP1, which is D.6. So, this gives us a way of connecting a transition on the analog comparator to the input capture register. Timer 1 is counting away at a rate which is dependent upon some new, yet another prescaler and multiplexer. When a transition occurs on the analog comparator, the values in T count 1 is snapshotted into ICR1. We could generate an interrupt. There's an interrupt source. We generate an interrupt off that capture signal. Go to the interrupt service routine, read our ICR1 directly in the interrupt service routine, and then we know the exact time at which the transition occurred. Any questions? Yeah.
Are OCR1 and D both connected to D5?
D5, did I say? I said, wow, that's weird. I think I said D4 and wrote D5. D4, sorry. Any other questions? Okay. So, we need to talk a little bit about how you set all this stuff up, so that, because there's a set of control bits for the analog comparator, and there's a bunch of control bits for timer 1 to set everything up so that the capture occurs and that the interrupts occur and everything's happy. So we got to plow through some control registers. TCCR1A is, of course, the timer control register, is one of the timer control registers. Two bits for COM 1A and COM 1B. Those are waveform generation control bits. The two lower bits are WGM11 and WGM10. This is the waveform generation mode. It controls normal versus pulse width modulator mode and clear on match on channel A, on match A. I haven't talked about pulse width modulator mode yet on any of these devices, on any of the timers, but it allows you to produce an analog output. We'll talk more about that for Lab 3. TCCR1B has 3 bits of clock select. This is pre-scalar, as it is with timer 0. Then this bit, well, let's say this bit first, which would be bit 6, sets the input capture. It's the ICES1. The input capture edge select channel 1. And if it's set to 1, it's rising. And if it's 0, it's falling. This is the ICNC1, which is the input capture noise canceller. Noise canceller. Basically, it's a digital filter that requires two measurements in a row to make sure that a transition actually occurred. So what we're going to do for this lab is you're going to choose a pre-scaler which is appropriate to the frequency you need to measure. You're going to turn on the input capture mode for either rising or falling. Doesn't matter. And you may or may not get better results with the noise canceller. You can try that. I don't think it's going to be too sensitive to that. Time mask 1 now has a couple of extra sources for interrupt service routines. You have TOIE1. That would be the timer overflow interrupt. That could be very useful in this lab because if you get an overflow, it means that you've certainly run the timer for too long and you've therefore are not going to get an accurate period. These two are the match bits. So this would be OCIE1B and OCIE1A. And then bit 5 is IC IE1, the input capture interrupt enable. That you're going to be very interested in, because when this interrupt goes off, it tells you that an edge has been detected and there is a value in the input capture register worth looking at. Conspicuously missing from all of this is any mention of the comparator. Well, it turns out that the comparator bits are in a completely different location called the ACSR. In the ACSR, there's a control bit to turn off the analog comparator. And this is weird. Setting a 1 here turns it off. So leave this at 0 if you're assuming you want to use the comparator. Bit 6 connects the positive input to a band gap reference. So if you turn this on, then B.3 no longer goes to the outside world. It goes to a band gap reference instead. You don't want that. You actually could use that in this case. It's your choice. Bit 5 is the raw comparator out. So that is in real time, nanosecond by nanosecond, changing with the value of the two input voltages. So it's like it's a little digital output of an analog comparator. 7, 6, 5. 4 is the comparator interrupt flag. Bit 3 is the comparator interrupt enable, which you are not going to want to turn on. You don't want to do that. You're going to use the timer 1 capture interrupt enable, not the comparator trigger interrupt enable. Bit 2 is what you've all been waiting for, I'm sure. It connects the comparator to timer 1. When this is on, the comparator becomes the trigger source for the timer 1 capture. And then these two bits determine interrupt on toggle, rise, or fall. So you have to set up both of these. You have to set up the timer 1 stuff. You have to set up the comparator. Once you do that, whenever you get a transition on the capture pin, actually on B.2, then you will trigger an interrupt, an input capture interrupt, which will store the time, which you will then read and save until the next time you get the capture interrupt. Subtract the 2, and that'll give you the period of the waveform coming in. So now we need to start talking about the code that actually does this, which happens to be one of the demo codes for Lab 1. Any questions? There's a big pile of terminology. It's all in the data sheet. Plus a whole lot more detail. So the example from Lab 1, which, yes, go ahead.
So the circuit, like the bit Q of the ACSR register.
Yes.
Is that like it when it's one, it takes like a comparator for the number one capture, right?
Yes.
So that's actually control for that mux, right?
It's the control for that mux, right? So this is ACSR.2, and when it has a value 1, it is the comparator, and when it has the value 0, it's input capture 1, whatever it is, B6 or something, yeah. So these peripherals are kind of a big toolkit that you can put together in all kinds of different ways. And you can think of all kinds of twisted things you can do with the comparator and the timer. And oh, by the way, the next version of these CPUs is called the X Mega. Allows you to have a complete switch matrix that allows any peripheral to be attached to any other peripheral without going through the CPU. I decided not to go to X Mega because I didn't think I could teach it in one semester. This is already complicated enough. So the example from Lab 1, do I really want to start? I'll start a little bit of this now. The example from Lab 1 then uses 3 timers in 3 different ways. Timer 0 is set up as a millisecond timer, boring, been doing that now for a week. Timer 1 is set up to capture the period of an incoming waveform, square wave. And timer 2 is set up to produce the square wave that we're going to measure with timer 1. And so some of you probably use the timer 2 code to generate a square wave for the beeping sound in Lab 1. And what we want to talk about now is then feeding back that square wave into timer 1 to measure its period. And the code I put online does that measurement 2 different ways. It uses the input capture register, directly with an interrupt, which is the preferred method, and then it uses a really cheesy low accuracy method, which polls the timer in real time. Whenever main notices a transition on ACO, the raw comparator output, ACO, whenever it notices a transition on ACO, it measures the period. And what we find is that about the best you can do with a 200 cycle square wave is about 10% accuracy if you poll ACO. If you use the input capture register directly, then you get cycle accurate. You get no error, 0 error. And so do not use the polled method to measure frequency in Lab 2. It's in the code merely as a straw man to say, look how bad this is. Not because I think it's a good idea to do it. Maybe I should have surrounded it with arrows. Now, rather than start in on the code, we have a few minutes. Let's talk some more about final projects. You'll hear this a lot. Anybody got any ideas? Hallucinations? Things you'd like to build? I've seen a flatbed plotter built out of the mechanical pieces were all struts from drop-in ceiling that the students found in the dumpster. All the mechanical stuff was cables and drive screws and pieces from the ceiling, from the dumpster. It was accurate. It was at less than 1 millimeter accuracy. They got the plastic gears out of the inside of whiteout bottles. Who knew? It was amazing. It was very good. And they did a flatbed scanner. It wasn't fast, but it was accurate. Had another group attempt to build a. They ran out of time. There's a general principle. If you're going to build something that has partly a mechanical piece and partly an electronic piece, build them at the same time, or build the mechanical piece first. Don't wait. Don't do the electronics first and then the mechanical piece. So what they did was they built the electronics to control the inkjet printer from hell, which was it was actually to write on sidewalks with sprayed chalk, and you were supposed to be able to set it down. It had a radial arm about 6 feet long that walked around and did a circular pattern, but the motor that did the walking didn't have nearly enough torque, and it wouldn't run. Very sad. In fact, it just sort of fell apart in lab. So you want to do the mechanical part at the same time you're doing the electronics. Don't wait till the last thing. If you have a really hot idea for recycling your old printer, your inkjet printer, start immediately on the mechanical part. We don't have many mechanical facilities, mechanical fab facilities in the lab. We have only light hand tools, a Dremel tool, which is a small grinder, a small rotary cutter, but nothing very heavy. And so if you need mechanical parts, you have to ask yourself, can you fab them? Do you have a way of building something? Because I don't. And what I recommend is that if you need, say, precision bearings or nice rollers, precision rollers or hinges, don't fab them. Go down to do engineering by walking around Lowe's or Home Depot, because houses are full of precision stuff, and you can find a lot of what you need for almost nothing in a home supply place. High pressure fittings. Had one, oh my God, what a mess. One year we had, it was very cool, but what a mess. We had people do an 8-channel water fountain. It was controlled by a fast Walsh transform, so it was so it did a frequency analysis, but not in Fourier space. It was a different space, different orthogonal transform, and squirted water out of these 8 jets in time with incoming music. And the first time they tested it, well, they tested it in the Phillips kitchen, right? And the first time, they had it pointed so it shot up, and there's water everywhere. So what they found is if they inverted it and shot it down into the sink, then it didn't make so much of a mess. But in that case, the high pressure fittings were all fittings they scrounged out of a lab someplace. The high pressure fitting, 30 psi fittings, and the solenoids were all out of a lab, and they didn't have to fab any of that stuff. They just screwed it together. And then they had to do the power circuitry to drive the solenoids to open and close the valves. And it became it was a nice math project to get fast Walsh transform going fast enough to. So you know what Fourier transform? It breaks down things into orthogonal sine waves. Fast Walsh transform breaks signals down into orthogonal square waves. It's ideal for a microcontroller because there's no multiplies. And there's no complex arithmetic. Think about it. Any questions? Any ideas for final projects?
We are considering building maybe walkie-talkie.
Walkie-talkies? So this would be digital. So you talk into an analog interface. It digitizes the signal, does the modulation into some encrypts it or something. So all you get is garbage out the other end unless you decrypt it. That could be fun. What frequency band? You have to be careful because ethically I have to make you follow FCC rules. Yeah. We can't have you blasting away on 2 meters along with every local radio amateur, right? Because the FCC will be on us. It turns out that 314 megahertz is an industrial control band, and you're allowed to transmit on that with a duty cycle of no more than 0.1%. Oh, man. So you have to go to 900 megahertz before you get to an unregulated band. So you either have to go to 900 megahertz, 916 megahertz, or 2.4 gigahertz. Do you know why Wi-Fi frequency 2.45 gigahertz is unregulated? Internationally unregulated. Why is it used? Do you know what frequency a microwave oven runs at? 2.45 megahertz. Why do you suspect that a microwave oven works? Because water absorbs 2.45 gigahertz radiation, right? That's why it heats water. It's an absorption line. And that's why Wi-Fi is good for near-end communication, because water absorbs it. And in Ithaca, that's awesome, because you get a range of 2-3 meters. But it's a limited range communication by design, and the reason it's limited communication is that all the water in the air absorbs the radiation. So you can go to 2.4, 5 gigahertz. I think there's an unregulated band. Anybody know for sure? I think there's an unregulated communication band at 5.
They use it on Wi-Fi now for a second.
5.8. Now it's also used for phones. And then above that, if you can figure out how to generate it, you can do almost anything you want above 10 gigahertz, as long as you stay out of the police radar bands. That's a bad thing to do, police radar band. So if you're going to transmit, think carefully how you're going to do it. Okay.